Good afternoon, everyone, and welcome to the session on an introduction to multidisciplinary engineering. We've got a few people still coming into the webinar as we speak, so I'm just going to pause until we've got a few more people. So if you do have any questions for Lean, please put them in the Q&A, and questions get posted into the Q&A under new, and are then published so that everyone else can see them, because otherwise it's just Lean and I who can see them and not the rest of the audience. So don't worry if your question is in the question and answer box and then suddenly it disappears, because it's just we've made it public. So I think we've got 43 attendees already. So it's my absolute pleasure to introduce you to Lean Jaban, who is a doctoral researcher at the University of Bath. She's in the Department of Electrical and Electronic Engineering, and her research is around designing sensory feedback for upper limb prostheses. She developed an appreciation of the importance of interdisciplinary engineering during her M.Eng in integrated mechanical and electrical engineering, and is expanding her understanding of how disciplines are interlinked by considering the psychological factors affecting the success of different designs in her research. On top of that, she's also an active member of WES at the University of Bath and is passionate about promoting engineering through outreach. It's now my pleasure for you to start, please. Thank you, Lee.
Thank you. So, I went to the last slide. Okay, I don't know why it was in the last slide, but yeah.
These things happen, I wouldn't worry.
Okay, so yeah, thank you. So as Elizabeth said, I'm a researcher at the University of Bath, working towards a PhD, and I did my integrated undergrad in integrated mechanical and electrical engineering at the University of Bath. So today I'm going to be talking about multidisciplinary engineering. The plan is to, first of all, give you an introduction about my journey, and then explain a bit what multidisciplinary engineering is, give some examples, and then link that to my research, and hopefully end with some tips. So to start with, I just want to say that actually my journey has been better than I expected. I'm currently doing exactly what I wanted to do 10 years ago. So when I was young, I watched this video about an amputee, a lower limb amputee, trying on a smart prosthetic limb, and seeing how happy they were made me dream of a day that I could contribute to that kind of research. Later on, when I wanted to decide what to do at university, I thought that mechanical engineering seemed like the way to go, and I applied to mechanical engineering, but afterwards I realized that mechanical engineering is not the only important part in designing prosthetic limbs. And I realized that there was a course at my university called Integrated Mechanical and Electrical Engineering. I always thought of electrical engineering as a scary topic because I couldn't see it, but I thought to go for it anyway, and I definitely do not regret my choice. I chose to do a placement as part of my degree, and I actually didn't get to do it anywhere related to what I wanted to do, but I did it at Rolls-Royce, who work on jet engines. I wanted to mention this because even though what they do actually has nothing to do with what I'm interested in, I did actually learn a lot. And that showed me that interdisciplinary engineering isn't just the basic types of engineering like mechanical, electrical, etc. you can actually learn from different fields. So, for example, their work focuses a lot on safety, which is an important thing in medical engineering as well. So yeah, after my placement and graduation, I started a PhD at the University of Bath, where I'm looking at sensor feedback for upper limb prostheses. So to talk about multidisciplinary engineering, so what it is basically just bringing together theories, concepts, and methods from different disciplines into a single context. So why is multidisciplinary engineering important? The reason is mainly because of the challenges facing us currently. There are lots of social, economic, and environmental and medical challenges, and they cause complex problems that are not that easy to solve just by focusing on one discipline. And this calls for engineers that are socially connected and aware of the different disciplines and fields to be able to come up with innovative solutions beyond the traditional ones. So based on that, the engineers need to develop skills that allow them to assess, understand, evaluate, synthesize, and apply perspectives and knowledge from different fields rather than their own. But this doesn't mean that we need generalist engineers that just know everything. Actually, we aim to be T-shaped engineers. So basically, this T is made of the horizontal and vertical lines, and the vertical line represents the expertise in one thing, and the horizontal represents general knowledge. So basically, engineers need to be aware of different things, but have to be an expert in one. And regardless of what degree you do at university, you can still be a T-shaped engineer. So for example, as part of my degree, it was a broad one. So I learned mechanical and electrical engineering, but towards the end, I specialized and developed that vertical line of the T-shaped engineer. Someone who chose a very specialized degrees, for example, biomedical engineering, can still develop this general understanding through talking to different people, attending seminars, and just having that mindset of understanding the different aspects or different fields. So why do we need T-shaped engineers? So this picture illustrates how T-shaped people help us communicate more effectively. So if you have a team with specialists that only know about their own field, they'll need someone who knows a bit about everything to help them communicate with each other. But if you've got T-shaped engineers working together, they can communicate with each other more easily. This picture also shows you that T-shaped people means that you can do more with the same number of people. So again, if you have very specialized engineers working together, sometimes some of those skills are not needed, and then others are more needed. So you need to have everyone, but not everyone is always working. But if you've got T-shaped engineers, you can be a bit more effective. So similarly, if you've got a bottleneck, you can rearrange the resources and help each other more effectively. So to give examples of how this works, the first one that came to mind was self-driving or even just electric cars, because this goes beyond, this shows you how this multidisciplinary engineering developed. So originally you had very basic mechanical cars that required mainly mechanical engineering. Then you had the self-driving cars. So that was where more electrical and power engineering came in. and understanding control systems. Then the next step was self-driving cars, and that is where you got artificial intelligence and trying to get the system to learn how to drive on its own. But it also goes beyond engineering, because you have to know how to program the system and take ethics into consideration in the decision making. So yeah, I struggle to think of examples beyond mechanical and electrical, because that is what I do. It just came naturally to me. But I found this to be an interesting example. So it's buildings in Tokyo that have special earthquake countermeasurements. And it's very interesting because it shows you that actually civil engineering, mechanical and electrical are very connected, because you've got the main structural design, the actuators, and the computer systems making it all work. The final example I've got that links a bit to my research because it's medical is the lab on chip. So for those of you who don't know, lab on chip is basically a chip that integrates laboratory functions on a single chip. And the point of it is to achieve high throughput and screening through screening and automation. So basically, instead of having people come to the lab, you bring the lab to them, put in the sample, and then have it all processed automatically. And the design of such chips includes obviously electronics, but also microfluidics to determine how the sample fluid will go to different sections of the chip. You also have got microelectromechanical systems, so MEMS, which are basically just really tiny mechanical structures. And obviously you've got chemistry as well, because of the reactions and making it work. So it's a very complex, small system. So moving on to my research, which as I mentioned is on sensory feedback for upper limb prostheses. Before I start, I just want to show you two quick videos that illustrate the importance of touch. So this is the first one, which is someone trying to light a match. So that is a healthy person trying to light a match. And you can see they can do it very easily. Now the second video is the same person, just seconds after, but with digital anesthesia. So basically they cannot feel what their fingertips are touching, but everything else is the same. And you can see that they struggle with this very simple task that they obviously know how to do very well. So yeah, you can see, keep on trying. But yeah, you finally do it in the end. So this shows you the importance of touch. And now going to my research, which is on sensory feedback for upper limb prostheses. Currently, upper limb prostheses do not allow amputees to feel what they're touching. So you'll have the limb attached to the residual limb. And then if it's a myoelectric or electrically powered one, you'll have sensors on this limb that detect muscle movements. So you basically flex one of your two muscles, and then the system detects that and generates, actuates the arm. And there's this quote from 1916, so 100 years ago, that says basically that artificial limbs will always displease the user because of that missing sensation of touch. it makes it difficult for amputees to use the prosthesis because they have to rely on looking at it and making sure they're grasping objects correctly. And 100 years later, this is still the case. You can see reports that demonstrate the rejection rates of upper limb prostheses, and it's quite high. So what I'm trying to do is provide that sensor feedback. So if you look at the picture, you've got like an arm band further up from the prostheses. So what I'm trying to do is to provide, through electrical stimulation, apply pulses that enable the amputee to feel what they're touching. So how does my research include different disciplines? So you've got the basic part, which is the electrical engineering, that enables me to design the system and connect it to the sensors and the arm itself and just make sure that everything works smoothly. You've got the neuroscience, which is what I spent quite a bit of time trying to understand, is to see how the nervous system works. So looking at that video, there's lots of research about the importance of touch and how the brain processes commands and how motor control works in the human body. And understanding that is essential to know what type of information you need to send to the user. And also it helps you understand how the signal should look like. So for example, the nerves encode intensity using frequency. So if you increase the frequency of the stimulation, the person will feel it as if the pressure is increasing. So that is an important part of the design that you need to understand in order to progress. So another bit is psychology, which is what I didn't expect to need to learn, but it's very important. As I mentioned, the rejection rate is quite high, and just providing feedback in a way that makes sense in terms of control does not mean that the users will like it. And actually, there is evidence of one device that was produced that wasn't very successful, and no one uses it because, well, that's not the main reason, but one of the reasons is not understanding the needs. So I'm carrying out qualitative research to understand exactly what the behaviors are that cause amputees to reject the prostheses and make sure I take that into account in my design. So a simple thing, an example, is that when you are asking them how they feel about it, instead of asking how natural does the sensation feel, you are reminding them that way that it is not natural and we're trying to make it natural. And this automatically gives a bad or negative impression. Instead, you can ask how comfortable does the sensation feel? And small things like that to actually result in a significant effect in the end. Moving on, I've got computational modeling. So obviously when you're trying things like that on human participants, you need to make sure that it's safe and okay. And as I mentioned, I've learned a lot about safety from my placement. So part of my research is computational modeling, trying it on models of the human body, making sure that what I'm doing makes sense. And finally, mechanical engineering is just to put it all together. It's a small part of my research currently, but it is still important. So that is about my research. If any of you are interested in learning about doing a PhD or anything, just, you can ask me in the questions and I can talk more about that. But for now, I've got some tips on multidisciplinary engineering in general. So if you want to become more of a T-shaped engineer, my tips would be to, first of all, work on your communication skills. So try to find opportunities to present to general audiences, whether it's through, if you have a women engineering society at your university, I would recommend trying to organize a seminar where different students can present, and this helps you work on your ability to explain your work to people from different disciplines. So whether you're the speaker or the attendee, that will be beneficial. So that links to the next bit. So widening your knowledge. If you hear about a seminar in a different department that is related to something you're interested in, don't be put off by the fact that it's not exactly related to your expertise. You can still learn from it. You can get ideas from different disciplines that complement each other. And my last tip is to participate in multidisciplinary projects or competitions. So at my university, I'm sure many do as well, we've got, for example, formula student teams and group business design projects that include students from different disciplines. So if you have that, just make sure you're talking and communicating to people from different disciplines. If not, maybe try to organize some, or for example, if you've got the Engineers Without Borders Society at university, they organize such events, competitions. But yeah, I just like the main message I want to bring across is you do not have to do an integrated degree in order to be a T-shaped engineer. You can work on your general knowledge personally. And yeah, that's all I've got. Thank you. I've put in my contact details, but I think they're there anyway.
Wow, thank you, Lynn. That's terrific. And I'm amazed and impressed that, you're saying that 100 years ago, people were saying people don't like a prosthetic hand because they can't pick things up. And that's still an issue today, and that you're dealing with it. And my own specialty is in systems engineering, systems thinking, which is the relationship between people and stuff. And so integrating kind of, the psychological effect, the physical, mechanics of it, and the sensory touching, as well as the electricals to do. It's just absolutely brilliant. We have a couple of questions in the chat, and we've got 6 minutes because I have to end this at 15:58 so I can start the next one. So the first one is from Carol Libans, who says, the graphics of your presentation are so nice. What did you use to make the presentation?
Actually, I think I found a template online that I used. But a side thing that I'm trying to do actually in my spare time is to learn Adobe Illustrator. So I've been creating diagrams for journal papers I'm working on. And I found that to be a nice way. It helps me to think about what I'm doing as I design the graphics.
Wow, you continue to expand your skill set as well. And Francis Hu has said, what advice do you have for someone starting research? I think it's a really excellent question. So
do you think that means like someone who's at the beginning of being a PhD student, or someone who's considering?
Well, I don't know specifically what Francis is asking for herself, but I think that if somebody is in their second or third year of their course, or maybe in their final year, I keep forgetting that engineering courses can be 4 years, that maybe they're thinking, actually, maybe what I want to do is go and do a PhD, go and do some research. And then if you could lead into what happens in your first year, because I think sometimes when you're at the beginning of your research program, it can feel a little bit daunting.
Yeah, definitely. So for me, I've always wanted to do work on prosthetics, but I never thought of research. I thought I'd work for a company that does prosthetics. But I think the main thing about if you're thinking about going into research is to make sure that you're really interested in the topic you are choosing. And I would do some research before applying to see what is out there. I would read some papers and just make sure that is the kind of thing you want to do. So that is the first step. Then if you want to do, like if you're not limited to doing it at your university, I would look at who are the leading researchers in that field and try to start contacting them early on, see if they are accepting PhD students. And as well as if they are, I would try to contact people who work with them, because the relationship with your supervisor is a very important one, and it can like make or break your PhD, in my opinion. You want someone who's supportive and doesn't make you work way too hard. So this is the sort of information you can get from talking to people, to their current students or postdocs. And then apply. So once you get it and start your PhD, I'm not sure if that's good advice, but I think don't stress too much about actually doing work as soon as you start your PhD. Just give it time and understand the literature properly. You don't want to start working and then realize someone's done it. I know you have your supervisor to guide that, but sometimes they're too busy and they're not aware of the latest research. So my tip would be to do a very good literature review first and plan, and don't get discouraged if you don't get much done in your first year. You're still understanding everything, and hopefully things will progress.
I would entirely agree. I spent 2 years on my MSc. It was a part-time degree, but you have to really like your subject, because if you're going to take at least 3 years, and sometimes it could be longer if you're part-time, you don't want to be at the year 4 or 5 thinking, oh my goodness me, I really can't stand discussing this element of engineering ever again. Do be passionate. I always say that the sweet spot for anything you do in life should be between what you like doing, what you're good at, and what you find easy. Because what you find easy, others may not. I can't draw for the hell of it. I mean, literally, gun at my head, draw something, I'm probably going to be a dead woman. So I'm not good at it, and I don't find it easy. But I am really, really good at speaking in public, which I know a lot of people find very difficult. So I think, you find that area of what you're good at, what you find easy, and what you enjoy. And that's probably going to be where your passion lies. Now, we do have one more question, but I've literally got 10 seconds to answer it. So, well, quickly, do you think you'll stay in academia after your PhD? Yes or no?
Not sure.
Good answer. Yeah, don't close doors before you have to, I say. And how do you communicate with disciplines outside of what you study, for example, psychology?
So I got in touch with a lecturer in psychology, and he's now my third supervisor. So he's helping me develop that side.
Absolutely. And great supervisors are hard to find, but once you find them, they're brilliant. I had one supervisor at the beginning of my course, and I had to defer for 3 months for personal reasons, but it meant that I ended up with another supervisor, and he was much better fit for me in terms of discussing. Well, thank you so much for your time, Lean, and for everyone else who's listening. I really appreciate it. And I'm now going to end the recording of this webinar and end the webinar. And the next one is Supporting Engineering Leaders of Tomorrow, or Sourcing Work Experience and Placement Opportunities, Top Tips. See you all soon.
Thank you.